So we need to look at the nature of light. Light has a wave nature and a particle nature. So we're going to look at the wave nature first. Light is a form of electromagnetic radiation, which is composed of perpendicular oscillating waves. One is the electric field and the other is the magnetic field. And an electric field is just a region in which an electrically charged particle, such as a proton or an electron or an ion, would experience a force. And a magnetic field is a region in which a magnetized particle would experience a force. And all of these electromagnetic waves move through space at the same speed, the speed of light, just 3 times 10 to the 8th meters per second. So here's a picture. So there's the electric component, and that's oscillating, going up and down in one plane. The magnetic component is oscillating in a plane that's perpendicular. But both of these are waves traveling in the same direction, and they're traveling at the speed of light. Everybody okay with that? Because this section is going to get weird too. We know that sound travels much slower than the speed of light. If you've ever seen lightning, you see the lightning, and then later you hear the sound, right? Because the light travels so much faster. Light travels 3 times 10 to the 8th meters per second. Sound is more like 340 meters per second, a lot slower. And so you can count the seconds between when you see the light and when you hear the sound, and you can estimate how far away that lightning strike was. It's kind of interesting.
Do you know what the actual measurement is? Because I was always told like 1 second equals about a mile or something like that.
Well, what I remember from a kid is counting to 8, 1001, 1002, 1003. When you got to 8, that was a mile. But we could do the calculation and figure it out.
Oh, need a sound.
Never mind, yeah.
50 miles per hour.
Well, it's 340, and so 340 meters per second and 3 times 10 to the 8th meters per second, and so you can figure out how much longer it would take sound to travel a mile than it would take the light, and that's how you would do that. Some measurements that characterize waves. The amplitude is how tall the wave is, and the wavelength is how far apart the waves are. So one crest to another. So wavelength is generally abbreviated with the Greek letter lambda, which is a little bit like an upside down lowercase y. The amplitude of a wave measures the light intensity. So light that is brighter has a higher amplitude than light that is dim. And here we've got another diagram. So here's the amplitude, how tall the wave is. Wavelength is how the distance between two waves. And waves in water behave in some of the same ways that waves of electromagnetic radiation behave. The advantage is that we can see them, right? So imagine going to the coast and standing on the edge of the ocean, and the waves are lapping up on your feet, and you're watching these big breakers come in, right? And so the amplitude is how tall are those waves. The wavelength is how far apart are they. You can see them out on the ocean. Then the frequency is going to be the number of waves that pass a given point in a certain amount of time. So if you're standing on the edge of in the wet sand there, you could count. And the frequency of ocean waves is rather low, so you wouldn't want to do it in a second because you would get less than 1. But maybe 5-10 minutes, and you could count how many waves crash on your feet, right? Frequency is given the letter mu, which is a V with a little curve in it, which is often confused with velocity. But anyway, that's the frequency. And the units of frequency are cycles or waves per second, which is also called hertz, and abbreviated capital HZ. Nothing to do with the rental car company. Hertz is cycles per second, or it's sometimes just per second. How many events per second? So waves carry energy. Light carries energy. The total energy is going to be proportional to how the amplitude of the wave, how tall it is, and how frequent it is. So if you think of standing in the, maybe you move out and you're knee deep in the water, right, at the coast. And if the waves are coming in and they're not coming in real frequently and they're low, you're going to be able to stand there, right? But if they're big, tall waves and they're coming very quickly, they're going to knock you over, right? They carry more energy. Waves carry energy. And the amount of energy depends on how tall the wave is, but also the frequency of the wave. For waves traveling at the same speed, the wavelength and the frequency are inversely related. Inversely related. So let's see if I can draw a decent wave today. So this wave has a short wavelength. The distance between two troughs is short, and this wave has a longer wavelength. If these two waves are traveling in the same direction at the same speed, which one is going to have more waves pass a given point? The one with the shorter wavelength. So short wavelength corresponds to high frequency. And this is the equation here. The frequency is equal to the speed of light divided by the wavelength. So if the wavelength is long, the frequency is short. If the wavelength is short, the frequency is high. Any questions about that? Oh yeah, here's the picture. I didn't actually have to draw them. So this has a shorter wavelength. It's going to have a higher frequency than this one up here. In terms of visible light, we perceive light of different wavelengths to be different colors. So red light, what we see as red, has a longer wavelength, a lower frequency than what we perceive as blue light, which has a higher frequency and a shorter wavelength. The amplitude affects whether the light is bright or dim, but does not affect the color. Any questions?
So is that why dogs see black and white? They don't see like that way?
So is that why dogs see black and white? I'm not sure if dogs actually do see black and white. They see colors differently than we see colors. And figuring that out is a whole nother complicated matter, isn't it? Yeah.
Is there like a maximum or minimum wavelength?
That you can see?
Not that you can see, the science.
Oh, that there is?
Like an ultra-charged gamma ray.
Yeah, so is there a maximum and minimum wavelength?
Or like a radio wave that no longer transmits anything.
So, when you take things to extremes, it gets kind of interesting, right? So if you take the wavelength to the long extreme, right, then you get something that appears to not have a wavelength because the wavelength was, what if the wavelength was 50 light years? How would you perceive that it's a wave? I don't know. Could there be something with a wavelength that long? There could be, I don't know. When you take wavelength to short distances, though, if you got down onto the order of, like, the size of an electron as the wavelength, I mean, I don't know. I kind of think there might be some sort of minimum, but I don't know.
But for amplitude,
For amplitude, well, the minimum amplitude would be not a wave at all. Maximum amplitude, I don't know. I don't know if there's a maximum amplitude. I mean, in infinity, That's kind of a painful thing to think
Big
about.
satellite.
You know, infinite. If the light had infinite amplitude, then it would have to have infinite energy, and it would have to have all the energy in the universe. Is the energy in the universe infinite? I don't think so. So I don't know that you can have infinite amplitude.
Well, if energy can't be created, destroyed, is it not infinite?
Well, the energy content of the universe is constant,
That's,
right? So that suggests that it's finite.
yeah,
So these are kind of fun things to think about, aren't they?
I think I just got so far behind.
This is exactly why we're so far behind in lecture, because we get to certain topics and you guys, get it, you wake up and you're like, ooh, and you ask questions. So, and I go along with it, right? So that's why we're doing this today. Color is just an interesting thing to think about. So the color of light is determined by its wavelength, which is related to its frequency. White light is composed of all frequencies of visible light. So the light from the sun is considered white light. Light from incandescent light bulbs, that's white light. Light from these fluorescent light bulbs is not white light because it's of how it's generated. If you take white light and pass it through a prism, you get a rainbow effect. You can separate the different wavelengths of light in the prism because of how they interact with the prism material. And what we observe is that the order of the colors is always the same. Red, orange, yellow, green, blue, indigo, violet. And so that's a good thing to remember. And you could think of it as kind of an odd name, Roy G. Biv. That's how I learned it. This is why you'll sometimes see a child's drawing of a rainbow, and you're like, there's something wrong with that rainbow, because they put the colors in the wrong order. So now you'll all be experts at drawing rainbows, right? You'll get your colors in the right order. So how are objects colored? What we perceive the color of an object to be has to do with the wavelengths of light that are reflected by that object. So in this picture, this girl's shirt is red. It's red because it is reflecting the red wavelengths of light, and it's absorbing the others. And so this is, all color is a combination of different colors put together. And you can play around with paint and food coloring and stuff and see that. So black objects absorb most of the light. It's very difficult to get a picture of a black animal, an all black animal. We used to have a black cat, and really hard to take a photograph of him because their fur absorbs the light. And on a picture, two-dimensional, they just kind of get lost. White objects reflect all of the light or most of the light. They absorb very little. If you've ever been out in the sun in the summer wearing a black shirt and another day been wearing a white shirt, which are you going to be warmer in, a black shirt or a white shirt? Black shirt. I feel sorry for my husband. He's got black hair. He goes out in the sun and I touch his head. It's like, ow, your head is hot. It's just black things absorb the light, and light contains energy. So black things warm up faster and white things warm up more slowly.
But didn't you just say that because like the wavelengths and amplitude, that's why we see those colors?
We see the colors because of how our eyes interact with light of different wavelengths.
Okay, so those wavelengths, why is it that only like say this object here only gives off like the gray wavelengths?
Because that gray thermos appears gray and reflects the grayish color because it's absorbing all the other colors.
So like you know how like most of our shirts here are cotton?
Mm-hmm.
Does that mean like each paint on it or chemical on it?
It's the dye on the cotton that absorbs or reflects and causes shirts to be different colors. And so, you take a shirt and you spill bleach on it, right, and the color goes away. What's up with that? The bleach destroyed the dye. The dye is an organic compound generally that interacts with light and reflects visible light and causes things to be colored.
I thought black would reflect every color.
No,
Reflect it.
black pretty much absorbs all the light.
But if you have like blue gloves, aren't they reflecting blue light
They're reflecting blue light,
and absorbing every other wavelength?
pretty much, yeah. Absorbing. So, blue nitrile gloves are blue because they're reflecting the blue wavelengths of light. I see you. And they're absorbing the others. There's no such thing really as black light.
Yeah, I mean, it's the absence.
Darkness is the absence of light. There's no such thing as darkness. It's just where there is no light. And so objects that appear to be black appear that way because they're absorbing the light and they're not bouncing it back to us.
Does a silver shirt reflect light better?
Well, silver things do reflect a lot of light, and there's different kinds of silver. Sometimes what we call silver is really more of a gray color, right? And sometimes silver is more like a mirrored finish. A mirror, or like chrome, reflects everything, and it reflects it so well that we can actually see the image reflected in it. But like this faucet here, we would say this is silver, right?
I see.
But that's not really not reflective in the same way that a mirror is, or chrome. Did you have a question?
Yeah, I'm a little confused by like how the color of light is like dependent on the wavelength and for the frequency and like the strength of the light.
The brightness of the light depends on the amplitude, how tall the wave is, but the frequency and the wavelength are inversely related because all light travels at the same speed. So if we go back to this picture, if we have both of these moving at the same rate, more of these crests are going to pass an observer in a given period of time than these, because these are longer. So this appears red to our eyes and this appears blue to our eyes because of the difference in wavelength. And that's a whole nother cool topic of how light interacts with the cells in our eyes and the rearrangements in molecules and how that sends signals to our brain, and we say, oh, that's a red shirt. Any other questions? So there are some, math problems we can do. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of that light. Well, we're given this wavelength, so maybe let's write that down. Lambda equals 515 nanometers. And they're asking me for the frequency. So, is there an equation relating those two things? Yes, there is. The frequency is equal to the speed of light divided by the wavelength. Well, the speed of light is 3.00 times 10 to the 8th meters per second. And the wavelength, we're going to want the wavelength to be in meters instead of in nanometers. A very easy way to convert this to nanometers is just to rewrite it, but using the meaning of the metric prefix instead of the metric prefix. So nano means 10 to the minus 9. So this is 515 times 10 to the minus 9 meters. That wouldn't be a good way to write down an answer because that's not proper scientific notation. But your calculator will still understand it, and so it's fine to use within a calculation. 515 nanometers. So 3 times 10 to the 8th divided by 515 times 10 to the minus 9. This gives me a frequency, 3 sig figs here, 5.83 times 10 to the 14. And what are my units? So the meters canceled out though. So what I'm left with is 1 over second, which can also be expressed as second to the minus 1 or hertz. And that is the unit of frequency. So 5.8 times 10 to the 14 wavelengths are going to pass a stationary point in 1 second. That's reasonable, actually, because this wavelength, 515 nanometers, really, really small. Very high frequency with the very small wavelength. Any questions? So visible light is electromagnetic radiation. It's only one small part of the entire spectrum. So we were asking earlier about, well, what's the maximum wavelength? What's a minimum wavelength? Well, we make use of a wide range of wavelengths of electromagnetic radiation. And this comprises the electromagnetic spectrum. Ranges from radio waves up to gamma rays. Gamma rays have the highest energy, and this high energy radiation has so much energy in it that it can damage biological molecules. It's called ionizing radiation because it actually will kick electrons out of molecules and atoms in your body and turn them into ions. And as you can imagine, that's not good. So, yeah, you got a question?
Kind of off topic, but what's
It's okay.
the purest form of energy? I thought about it like
What's the purest form of energy?
heat or light. Like which, or is there something else you think it would be?
That is off topic.
Yeah, I'm sorry.
It's okay. I will try to think about that later.
Okay.
Yeah, it's a good question. So here's the electromagnetic spectrum. So we have frequency in hertz listed here, going from low frequency to high frequency. In the middle here we have the names of these different sections. Down here we have wavelength. So the wavelength goes from long to short, because there's a direct relationship between the frequency and the wavelength, because all of this stuff is moving at the speed of light. So then from this little tiny portion here, we've blown it up because we are interested in visible light. That's what we can see. Visible light ranges from about 750 nanometers for red up to about 400 for violet. This is higher energy, this is lower energy. It's just that tiny portion in here. Above the visible light, above violet, we have ultraviolet. What does ultra suggest? Super, better, more, right? This is ultra-tide or ultra-dawn liquid, right? Ultraviolet is more than the violet. It's more violet than violet. So this is on the violet end. Over here, on the other side of the visible light, we have infrared. That is below the red on this line. I think of this as going from low to high, left to right. So ultraviolet is above, infrared is below. We're familiar with ultraviolet. These are, this is electromagnetic radiation that comes down in the sun along with visible light and gives us a nasty sunburn if we stay out there too long. If you continue on to higher frequency, shorter wavelengths, higher energy, you get into X-rays. Those are the X-rays they use to check your teeth and check your broken arm. and above that is gamma rays. Gamma rays have positive uses, but they're also really, really dangerous. And going this way towards lower energy is infrared. Infrared is heat. So anything that's warmer than its surroundings, will give off infrared radiation. So we're all sitting here emitting infrared radiation right now. Because the room is, what is the room today? 72.5, and I'm pretty sure your temperature is warmer than that or you'd be dead. Lower in energy, microwaves. Now, does it seem odd that microwaves would be less energetic? What do we use microwaves for? Heating our food. How does that work? Well, the reason that microwaves heat your food is that that is a frequency that is easily absorbed by water molecules. So the water molecules have this unusual ability to absorb energy in that frequency range. And when they absorb that energy, their thermal energy increases and they make your food hot. And then below this we get into radio waves. There's cell phones, FM, and TV, and then AM. AM radio has a very long wavelength, like on the order of 100 to 1,000 meters. That's a long wavelength. AM radio waves can travel very long distances. So you should read about these in the textbook. I'm not going to tell you all that stuff because you can read. Any questions? So a continuous spectrum is one that contains all the frequencies, all the wavelengths. So we see that with white light, such as from the sun. We get a continuous rainbow. And this is kind of out of order here. This is a thermal image using infrared light. You've probably heard of night scopes and night vision. So at night, there's very little visible light. We can't see because there's not any light to bounce off the objects, and so we can't see them. But warm things are always emitting infrared radiation. We can't see it with our eyes, but we can design detectors that can sense it. And so you can take pictures like this. And then we just assign colors to different levels of infrared radiation. And so this is a picture of a guy and with his 3 dogs. And we can see his face and his legs. He's wearing shorts. I've seen the actual photograph in other books. These are warmer. And the background is blue. That's cooler. And you look at the dog. And is the dog's nose cold or warm? Cold. Dog's nose is cold. Eyes, the insides of his ears, around his mouth is warm. Here where the fur is thick, it's trapping that infrared radiation. It's not getting out.
That type of image probably would work during the daytime, right?
It should work during the daytime as well, because the infrared radiation is still there. It's an odd thing to think about, isn't it?
I know, because the sun, if it gives off heat, wouldn't it just...
It'd be hard to make out.
It could possibly be harder to make things out because when the sun hits things and warms them up, they will radiate heat. But if you're looking for living organisms, especially mammals, they're generally going to be warmer than their surroundings, or they may be cooler than their surroundings. And so the wall may be hot, but you see the person is cool in front of the wall. But they're generally used at night because during the day, visible light works a lot better. Any other questions? Yeah, I need to work on these slides. Okay, one thing that waves can do is they can interfere with each other. They can do so in a constructive way or a destructive way. So constructive interference occurs when waves are in phase. Their peaks line up and their troughs line up. And then they get larger in amplitude. They can also interact destructively Destructive interference is when a peak lines up with a trough and they can essentially cancel themselves out. So here's a picture. So two waves in phase essentially add together and the amplitude becomes larger. Two waves out of phase add together to nothing. And this is the same sort of thing that happens on a trampoline. You got one person jumping up and down, and if the other person, especially if they're smaller, bounces just right, they can take advantage and get shot up much higher, right? But if you bounce exactly wrong, then you don't go anywhere at all. And that's constructive and destructive interference of the waves that you're making when you're jumping on the trampoline. This happens with light. It can happen with sound. I've heard of noise canceling headphones or noise reduction headphones. What they do is they have a sensor that detects the noise around you and then generates a signal that is out of phase with that noise and transmits it to your ears. And so it cancels out the noise on the outside. It's a pretty neat idea. So waves can interfere. Waves can also diffract. When waves encounter an obstacle or they encounter an opening in a barrier, they can bend around that. And we'll have some visual illustrations of that in a little bit. So waves diffract. Traveling particles do not diffract. If you throw a baseball near a pole, being close to the pole is not going to cause the trajectory of the baseball to change. But if you have a pole in the swimming pool and you've got waves coming, the presence of that pole will cause the waves to change shapes. If we have two slits that we allow the light to go through, and they are separated by a distance that's on the same order as the wavelength of the light, then we can get an interference pattern caused by those diffracted waves. And that interference pattern is characteristic of all light waves. So this is what's going on here. So here we have wave crests. The lines, the pink lines here are representing the crests of the waves. So the waves are traveling this way. They're nice and straight. They hit this opening, and the waves that come through now are diffracted. They're bent. Particles don't do that. If you have particles going at the same barrier, the particles that hit the barrier are going to stop or bounce back. The particles that hit the hole, the slit, are just going to go straight through, and their behavior is not affected. So if we have light coming from a single source, the waves emanating from that source are all going to be in phase with each other. And then if we have that light pass through two slits, as the waves pass through the slits, they diffract. And the diffraction, these get wider and wider, and they're going to overlap with the diffracted waves over here. And in some portions on this screen, we're going to have them overlap in a constructive way, and we'll get a very bright spot. And other places, they will overlap in a destructive way, and we'll get a dark spot. And this is called a diffraction pattern. And this is what light does. This is what waves do. And you can see it with waves in the water as well. Any questions? So we're going to watch a cool video now, and then we'll talk about this some more.